Naturally derived products are everywhere. They are in our diets, our medicines, our agriculture, and many of the everyday products that we rely on. Yet producing these compounds at scale remains a major challenge. Many are extracted directly from plants or other organisms, which can limit supply and strain natural resources. Others require complex, multi-step chemical synthesis that is costly, environmentally disruptive, and difficult to scale efficiently. Even when demand is high, production bottlenecks can keep supply low and prices high. We have seen how transformative scalable production can be. An example of a natural product is insulin, which is extracted from animal sources in a slow and limited process. Artemisinin is another example, serving as an anti-malaria drug produced in sweet wormwood. But extracting it from plants is a complex process. Today, these can be produced in microbes, revolutionizing how we obtain these natural products, thereby improving reliability, affordability, and global accessibility. From this, our team has set out to investigate other natural products faced with such limitations. Microorganisms such as E. coli have long been leveraged to serve as biological factories capable of synthesizing complex molecules in a controlled and scalable manner.
Here, as part of the University of Lethbridge iGEM team, we are utilizing a predictive model-guided strategy towards developing optimized microbial systems specialized in the biosynthesis of a range of different natural products. Our optimized E. coli systems will be geared towards 4 groups of natural products: terpenoids, polyketides, phenylpropanoids, and alkaloids. Currently, these products are difficult to produce in microbes due to limitations in precursor availability, cofactor imbalance, pathway toxicity, and regulatory incompatibilities between heterologous pathways and native cell metabolism. Therefore, our first strategy will use a mix of predictive modeling and bioinformatics, which are computational programs and software that can interpret complex biological data to perform a cell-wide search to find genes to target and help inform our strategies for modification within the E. coli's metabolic pathway, the path that resources take in to the cell to become usable final products.
In this case, we aim to use software and programs that can add mutations into our potential target genes, as well as simulate how changing this enzyme will affect the metabolic pathways it is a part of. By simulating how modifying these genes can affect their respective products, we can understand more about their impact on the metabolic pathways and incorporate these changes in the lab accordingly.
Think of the cell like a city with many roads, intersections, and traffic lights. Each car represents cellular resources, and each destination represents a different metabolic product. Some roads lead to destinations we do not care about. These are competing pathways. To reduce traffic going in those directions, we simulate decreased catalytic activity by turning the traffic lights red more often, or making those roads smaller and harder to travel. This way, fewer cars take those routes, so fewer resources are used there. At the same time, the road leading to our desired natural product is the destination we want to prioritize. For this pathway, we simulate increased efficiency by turning traffic lights green more often, widening the road, and creating smoother intersections. This allows more cars to flow more quickly and efficiently towards the desired destination. By carefully controlling traffic lights, slowing down unwanted routes, and speeding up the preferred route, we direct traffic without shutting down the whole city. This targeted control improves the number of cars reaching the desired destination, increasing product yield while maintaining smooth traffic flow and overall cellular robustness.
With our identified target selected, our team will transition into the Wetlab to introduce edits into the E. coli to validate our predicted modeling towards our optimized microbial system. Our team will leverage tools such as multiplex automated genome engineering, or MAGE, technology, which can simultaneously target our identified targets within the E. coli. This allows us to incorporate the modifications previously identified in our modeling and simulation phase throughout the genome simultaneously, creating a bacterial strain that would provide us with increased yields in producing our desired natural product. Utilizing MAGE will allow us to generate diverse strain variants rapidly and efficiently, and allow us to select for variants that provide us with the best yield in producing our desired natural products.
The goal is not simply to optimize E. coli strains for one product. We aim to build a set of specialized production chassis, a robust microbial platform that can be adapted to synthesize multiple naturally occurring compounds. By creating this chassis, we streamline future strain development and reduce time and cost to bring new products to scale. Our innovation lies in integrating predictive metabolic modeling with multiplex genome editing to accelerate and refine strain optimization. Beyond efficiency, there is a sustainability imperative. Microbial biosynthesis reduces reliance on overharvesting, lowers land and water use, and minimizes environmental damage from complex chemical synthesis. By improving production efficiency, we support more responsible consumption and manufacturing practices, aligning with Sustainable Development Goal 12. By combining computational prediction with automated genome engineering, we are engineering more than a microbe. We are building a scalable, sustainable platform for the future of natural product biosynthesis.